Somewhere inside NASA's vast digital archives, there's a photograph that almost nobody on Earth has truly stopped to think about. It is not the kind of image that makes the front page of a magazine. There are no vivid colors, no dramatic explosions, no sweeping panoramas of alien landscapes catching the light of a distant sun. It is dim. It is monochrome. It shows a planet draped in near total darkness, its silhouette barely visible, illuminated only by the cold, ghostly light reflecting off its own rings. And it was captured at exactly 12:58 in the afternoon, on September 14th, 2017, by a spacecraft that knew, in the only way a machine can know anything, that it had hours left to live. No rescue was coming. No return trajectory had been plotted. The mission controllers back on Earth had made their decision, and it was final. A spacecraft that had traveled more than 4 billion miles through the void, that had survived 2 full decades of radiation, gravitational punishment, and the bone-chilling cold of deep space, that had rewritten entire chapters of planetary science, pointed its camera one last time at the world. It had spent 13 years studying, held that image for a fraction of a second, and then fell silently into the clouds of Saturn, burning like a meteor, dissolving into the planet it had come to know better than any instrument in human history. What it left behind in that moment was not simply silence. What it left behind was a question so enormous, so unsettling, so unavoidable, that we have spent the years since its death either grappling with it or, more troublingly, looking away from it. Most people, if they remember Cassini at all, remember a headline. They remember a short clip of scientists weeping in a control room in Pasadena. They remember scrolling past an image of Saturn and thinking beautiful and moving on with their day. What the mainstream coverage almost never communicated, what got buried beneath the spectacle of the farewell, is that what Cassini actually found in its final years fundamentally changed the nature of the most important question human beings have ever asked. Not just expanded our knowledge, not just added data points to existing models, but changed the question itself. And that is something entirely different. To understand why, you have to go back to where this story begins, because the beginning is just as extraordinary as the ending. On October 15th, 1997, a spacecraft roughly the size of a school bus was launched from Cape Canaveral on top of a Titan Ivy B rocket. It carried 12 scientific instruments, nearly 33 kilograms of plutonium dioxide, to power its systems through the darkness of the outer solar system. And the collective ambitions of more than 5,000 scientists and engineers from 17 nations. Its full name was Cassini-Huygens, a joint production of NASA, the European Space Agency, and the Italian Space Agency. The Cassini part honored Giovanni Domenico Cassini, the 17th century Italian-French astronomer who first observed the gap in Saturn's rings back in 1675. The Huygens part honored Christian Huygens, the Dutch mathematician and astronomer who, in 1655, became the first person to correctly identify that Saturn was surrounded by a system of rings, rather than the strange flanking appendages that had confused Galileo when he first spotted them through his crude telescope decades earlier. The mission was going somewhere no controlled spacecraft had ever gone to stay permanently. It was going to Saturn. And given the distances involved, the laws of orbital mechanics, and the spacecraft's limited fuel supply, it was going the long way around. Engineers charted a trajectory that swung Cassini past Venus not once, but twice, then back past Earth for a gravity assist, then, like a cosmic slingshot, hurling the probe faster and further into the outer solar system without burning any of its precious onboard fuel. The whole journey took 7 years. 7 years of drifting through interplanetary space, crossing billions of miles, sending back occasional check-in signals to a waiting team on Earth, before the spacecraft finally arrived at Saturn on June 30th, 2004. At that moment, it had to fire its main engine for exactly the right duration to shed enough velocity to be captured by Saturn's gravity. Too short a burn and Cassini would sail right past the planet and vanish into deep space forever. Too long and it would dive too deep and be lost. The team at the Jet Propulsion Laboratory sat in near silence during those engine burn minutes, knowing that the signal delay between Saturn and Earth meant that by the time they received confirmation, the moment itself was already long over. Either Cassini had made it into orbit, or it was already gone. When the confirmation arrived, there were tears, not because something difficult had been accomplished, because something impossible had been achieved. What they found waiting for them when they arrived, though, was nothing like what anyone had expected. In early 2005, during one of Cassini's first close approaches to Saturn's smaller moons, the spacecraft swung near a body called Enceladus. It was a small moon, barely 313 miles across, roughly the diameter of the state of Arizona. Scientists had noted it before as unusually reflective and bright, but that was essentially all it was supposed to be. A frozen, geologically inert rock orbiting Saturn in the cold dark. What Cassini's instruments detected instead stopped the mission team cold. Coming from the moon's south polar region, from a series of long parallel fractures in the ice that scientists would later nickname the tiger stripes, were geysers. Not metaphorical geysers, not ancient geological remnants, but active, ongoing, enormous eruptions of water vapor, ice particles, and gas blasting hundreds of kilometers into space. Liquid water, actively erupting. Right now. More than 886 million miles from the sun, in a part of the solar system so cold and remote that water was supposed to exist only as permanent, unchanging ice. The implications of that discovery did not arrive all at once. They arrived the way the most profound realizations tend to arrive. Slowly, incrementally, each new piece of evidence deepening the shock of the one before it. If water was erupting from Enceladus, there had to be a reservoir. If there was a reservoir of liquid water, there had to be a heat source keeping it from freezing. And if there was a heat source inside a moon that receives almost no solar energy whatsoever, then something remarkable was happening beneath that ice. The mission team revised Cassini's flight plan. They aimed the spacecraft directly at the plumes. They flew through them. They pointed every instrument aboard at those geysers and let the data stream back across 800 million miles of space, year after year, building a portrait of a world that had no right to exist the way it did. What that portrait revealed, piece by piece over the following decade, was staggering. Beneath a shell of highly reflective ice somewhere between 16 and 19 miles thick, Enceladus harbors a global saltwater ocean. Not a buried lake, not a localized pocket of meltwater, but a full planetary ocean encircling the moon's rocky interior. An ocean estimated to contain roughly a tenth of the water volume of the Indian Ocean here on Earth. The water tests as alkaline and contains sodium chloride, ordinary table salt, which is geologically significant because it tells scientists the ocean is in direct, ongoing chemical contact with the rocky seafloor beneath it. And at that seafloor, the thermal signatures and chemical data point unmistakably toward hydrothermal, vent activity. The same hydrothermal systems that exist along the mid-ocean ridges on Earth's seafloor, the same systems that, on our planet, support entire ecosystems of life that never see sunlight, organisms that survive purely on chemical energy drawn from the heat of the Earth's interior, tube worms, thermophilic bacteria, organisms unlike anything that lives near the surface, thriving in conditions that would seem impossibly hostile to most life we know. In October of 2015, Cassini made its deepest ever dive through the Enceladus plume, passing within 49 kilometers of the surface. The spacecraft's ion and neutral mass spectrometer, an instrument designed to analyze the chemical composition of gases the way a trained bloodhound follows a scent trail, detected molecular hydrogen pouring out of the plume in quantities that could not be explained by any passive geological process. There was simply too much of it. The only mechanism capable of producing that volume of hydrogen is an active hydrothermal reaction happening at the seafloor in real time. Hot rocky material reacting chemically with circulating ocean water in a process called serpentinization. The research based on that flyby, published in the journal Science in April 2017, went further. The concentration of molecular hydrogen detected was high enough that if microbial life existed in that ocean, it could theoretically use that hydrogen as an energy source through a metabolic process called methanogenesis, the exact same process used by certain microorganisms on Earth's ocean floors. The lead author of that paper, Dr. Hunter Waite of the Southwest Research Institute, was careful in his language, as scientists are trained to be. He stated that while they had not found direct evidence of microbial life, the discovery of hydrogen and the evidence for active hydrothermal chemistry offered what he called a tantalizing suggestion that habitable conditions exist beneath the moon's icy crust. Scientists do not use the word tantalizing casually. Within the constrained vocabulary of peer-reviewed science, that word carries an enormous weight. It was as direct a statement as the scientific community's conventions permit. This place might be alive. But Enceladus was only the first revelation in what would become a cascade of them. Because while Cassini was dismantling everything we thought we knew about the inner moons of Saturn, it was simultaneously constructing an entirely separate and equally mind-bending case about the largest moon in Saturn's system, a moon called Titan. Titan is unlike any other body in the solar system, and that is not an overstatement. It is the only moon orbiting any planet in our solar system that possesses a dense, complex atmosphere, an atmosphere denser, in fact, than Earth's, with surface atmospherics. Pressure about 1.5 times what you would feel standing at sea level on this planet. That atmosphere is thick with nitrogen and methane, and it does something that no other moon in the solar system does. It produces weather, real weather. Clouds form in Titan's orange sky. Rain falls. That rain flows into rivers that carve channels through the landscape. Those rivers empty into lakes and seas that sit placidly at the surface, calm enough to reflect the distant point of light that is the sun. But none of this weather system involves water. The liquid that drives Titan's entire hydrological cycle is methane and ethane, hydrocarbons that on Earth exist as natural gas, But on Titan's surface, where temperatures hover around minus 290 degrees Fahrenheit, they behave exactly as water does on Earth. The largest known sea on Titan, a body called Kraken Mare, located near the North Pole, is estimated to contain more liquid hydrocarbon than the total combined proven oil and gas reserves of every country on Earth. Let that number sit for a moment. One sea on one moon of Saturn contains more hydrocarbon liquid than all the fossil fuels we have ever found or ever expect to find on this entire planet. In January of 2005, the Huygens probe, which had been riding inside Cassini since the beginning of the mission, separated from the main spacecraft and began a descent through Titan's thick orange atmospheric haze. For over an hour, it parachuted downward, transmitting data through the mothership back to Earth before touching down on what turned out to be a flat plain covered in rounded ice pebbles, pebbles that had clearly been shaped and smoothed by flowing liquid over long periods of time. That landing was the most distant surface touchdown in the entire history of space exploration, more than 750 million miles from Earth. And the chemical environment it found on that surface has been generating scientific questions ever since. Titan's chemistry is not just complex, it is almost disturbingly so. Cassini detected large negatively charged organic molecules in Titan's upper atmosphere, molecular species that by rights should react almost immediately with surrounding materials and disappear. They had no business being there at the altitudes where they were found, yet there they were. And as they drifted slowly down through the atmosphere over millions of years, settling onto Titan's surface, they were building up a chemical inventory unlike anything else we have observed anywhere else in the solar system. An inventory rich enough in organic complexity that some researchers have proposed that Titan may be acting as a kind of slow-motion laboratory, running a version of the chemistry that preceded life on early Earth, playing out on geological timescales, not biological ones, but playing out nonetheless. What Enceladus and Titan together forced the scientific community to confront was a fundamental revision of the framework through which we had been searching for life in the universe. For most of human history, and certainly for most of the history of the space age, the working assumption had been that life required a very specific set of conditions: liquid water on the surface, the right kind of star at the right distance, a protective magnetic field, a stable long-term climate. We searched for Earth-like planets around sun-like stars, and we called that the habitable zone, the Goldilocks band, where conditions were just right for life as we knew it. And for a long time, that framework seemed reasonable, until a spacecraft flew through a geyser on a frozen moon 886 million miles from the sun, and everything we thought we understood about what habitable means needed to be rewritten. Enceladus had none of Earth's surface conditions. It was frozen, it was dark, it was tiny, it was a place we would never have pointed a telescope at while looking for life. And yet it possessed every interior condition that life requires: liquid water, chemical energy, minerals, heat, organic chemistry, all of it hidden beneath the ice, screaming into space through those south polar vents, as if the moon itself was trying to tell us something. We had spent decades asking where else in the universe might conditions be like Earth's. Cassini turned around and told us we had been asking the wrong question. Then came 2017, and what mission controllers at the Jet Propulsion Laboratory called the grand finale. By that spring, Cassini had been in orbit around Saturn for nearly 13 years. It had completed 294 orbits of the planet. It had captured more than 450,000 images. It had discovered 6 previously unknown moons and returned a volume of scientific data that would take decades to fully analyze. But its fuel was nearly exhausted, and the team faced a choice that was not really a choice at all. If they allowed Cassini to run out of fuel without a controlled disposal, the spacecraft might eventually drift into Enceladus or Titan through random orbital decay, potentially contaminating those worlds with terrestrial microorganisms that had survived the 20-year journey clinging to the spacecraft's surfaces. The planetary protection protocols that govern all deep space missions were unambiguous. Cassini could not be allowed to contaminate the very worlds it had revealed as potentially habitable. The spacecraft would have to be destroyed deliberately, intentionally guided into Saturn's atmosphere, where it would burn up completely, leaving no trace. But before it died, it would do something unprecedented. Beginning in April of 2017, Cassini began a series of 22 successive dives through the gap between Saturn's innermost ring and the top of the planet's atmosphere, a gap approximately 100 miles wide that no spacecraft had ever entered before. The mission team called this the grand finale. They were not entirely certain Cassini would survive the first pass. Models had suggested the gap might be filled with ring particles dense enough to sandblast a spacecraft into silence. What they found instead was that the gap was almost completely empty. Unexpectedly, mysteriously, profoundly empty. And the data Cassini returned from that intimate proximity to Saturn itself, closer than any spacecraft had ever been, produced 3 more discoveries that shook the scientific world. The first involved the rings themselves. Since Galileo first noticed through his primitive telescope in 1610 that Saturn had some kind of strange appendages on either side, astronomers had generally assumed that the rings were as old as the planet itself, roughly 4.5 billion years old, dating back to the formation of the solar system. They seemed so fundamental, so iconic, so permanently part of Saturn that it was difficult to even imagine Saturn without them. Cassini's gravity measurements and dust sampling analysis during those final dives demolished that assumption completely. Analysis of the data published in the journal Science in January 2019 showed that Saturn's rings are somewhere between 10 million and 100 million years old, not 4.5 billion years, somewhere between 10 million and 100 million. In geological terms, those rings are brand new. They may have formed during the Cretaceous period. Saturn itself has existed for billions of years, but those magnificent rings, the feature that makes Saturn the single most visually striking object in the solar system, are a recent addition to a very ancient world, more than 750 million miles from Earth. And the chemical environment it found on that surface has been generating scientific questions ever since. Showed that Saturn's rings are somewhere between 10 million and 100 million years old, not 4.5 billion years, somewhere between 10 million and 100 million. In geological terms, those rings are brand new. They may have formed during the Cretaceous period. Saturn itself has existed for billions of years, but those magnificent rings, the feature that makes Saturn the single most visually striking object in the solar system, are a recent addition to a very ancient world. These instruments detected instead stopped the mission team cold. Coming from the moon's south polar region, from a series of long parallel fractures in the ice that scientists would later nickname the tiger stripes, or geysers. Not the entire hydrological cycle is methane and ethane, hydrocarbons that on Earth exist as natural gas, but on Titan's surface, where temperatures hover, dense, complex atmosphere, an atmosphere denser orbiting any planet in our solar system that possesses a dense, complex atmosphere, an atmosphere denser, in fact, than Earth's, with surface atmospherics pressure about 1.5 times what you would feel standing at sea level on this planet. That atmosphere is thick with nitrogen and methane, and it does something that no other moon in the solar system does. It produces weather, real weather. Clouds form in Titan's orange sky. Rain falls. That rain flows into rivers that carve channels through the landscape. Those rivers empty into lakes and seas that through Titan's thick orange atmospheric haze. For over an hour, it parachuted downward, transmitting data through the mothership back to Earth, before touching down on what turned out showed that Saturn's rings are somewhere between 10 million and 100 million years old, not 4.5 billion years, somewhere between 10 million and 100 million. In geological terms, those rings are brand new. They may have formed during the Cretaceous period. Saturn itself has existed for billions of years, but those magnificent rings, the feature that makes Saturn the single most visually striking object in the solar system, are a recent addition to a very ancient world. These instruments detected instead stopped. That rain flows into rivers that carve channels through the landscape. Those rivers empty into lakes and seas that through Titan's thick orange atmospheric haze. For over an hour, it parachuted downward, transmitting data through the mothership back to Earth, before touching down on what turned out showed that Saturn's rings are somewhere between 10 million and 100 million years old, not 4.5 billion years, somewhere between 10 million and 100 million. In geological terms, those rings are brand new. They may have formed during the Cretaceous period. Saturn itself has existed for billions of years, but those magnificent rings, the feature that makes Saturn the single most visually striking object in the solar system, are a recent addition to a very ancient world. More than 886 million miles from the Sun, in a part of the solar system so cold and remote that water was supposed to exist only as permanent, unchanging ice, blasting hundreds of kilometers into space. Liquid water, actively erupting. Right now, more than 886 million miles from the Sun, in a part of the solar system so cold and remote that water was supposed to exist only as permanent, unchanging ice. It is also something else. It is a mirror, a dim, cold, monochrome mirror pointed back across 894 million miles of space, at a small blue planet where a species with the intelligence to build Cassini and the curiosity to send it and the wisdom to understand what it found has still not fully answered the question the mission made unavoidable. Are we alone? That question now has coordinates. It has a target. It has a moon, 313 miles across, covered in reflective ice, orbiting Saturn, shooting its own ocean contents into space twice a day through fractures in its south pole. The answer, if there is one, may already be drifting through that plume, suspended in ice crystals, waiting for a mass spectrometer sensitive enough to read it. We have built the technology to ask the question properly. We have not yet committed to asking it. The longer we wait, the more that hesitation becomes a statement. Not about what we know, but about who we are, about what we value, about whether we are genuinely serious when we say we want to know our place in the universe, or whether we are content to ask the question from a safe distance where the answer can never quite reach us. Cassini showed us that the universe does not keep life only on Earth, does not concentrate biology only on worlds that look like ours, does not reserve the conditions for existence only for planets in the comfortable middle distance from sun-like stars. It told us the universe is far stranger, far more generous, and far more full of possibility than we had allowed ourselves to imagine. And then it fell into Saturn's clouds, and it went silent. But silence is not absence. Somewhere out there right now, those plumes are still erupting. That ocean is still circulating. Those hydrothermal vents are still warming the seafloor. Whatever might be living there, if anything is living there, has no knowledge of us, no awareness of the spacecraft that discovered it, no concept of the question hanging in the mind of the species that built that spacecraft and watched it die on a September morning in 2017. It is just living, or not, existing, or not. Waiting without knowing it is waiting. The mission is over. The machine is gone. The silence is complete. But the question is louder than it has ever been. And somewhere in 635 gigabytes of data, in the chemistry of an icy moon's south polar plumes, in a global ocean that has never seen sunlight, the answer may already exist. We just have to care enough to go and find it. Before we forget what Cassini showed us. Before the funding dries up and the urgency fades, and we convince ourselves once again that the void is empty and we are alone, and the silence means nothing. Because we made that assumption once before. And then a spacecraft flew through a geyser erupting from a frozen moon in the outer solar system, and the universe looked back at us and proved us wrong.